11.3 is called areas of polygons. It starts off with rhombuses and kites, and you got to remember one of the properties of diagonals of rhombuses and kites, and that's they are perpendicular. Okay, so in my diagram here, this is not exactly to scale because I did, but it shows that this is a rhombus, right? Because all four sides are congruent, and so therefore I know that the diagonals are all perpendicular. Okay, and that makes it a lot easier to find the area of this whole rhombus because I've just got four right triangles. So if I take, say, this triangle, for example, I could find the area of this triangle with 1/2 base times height. So the base and height pair could be 2 and 5 because they're perpendicular. So this is half of 10, which is going to be 5. So one of those triangles has an area of 5 units, and there's four triangles just like that because they all have base and height pairs of 2 and 5. So then I can say that the area of the rhombus would just be 4 times 5 because there's four triangles just like that. And so this is 20. I don't know the units here, but I still want to show that the units are squared because it's area. So there's the area of that rhombus. Okay. So let's look down to the next example. So this one's a kite, and again, when a kite also have perpendicular diagonals. So this time I've got I can use this triangle. And that triangle is going to have the same area as this one. Okay, the other two triangles are smaller. And so those two ones that I colored blue are going to have the same area to each other. But I got, two small triangles and two big ones. So I could find the area of this, which would be half of 15, which would be 7.5. And so this one's going to be 7.5 as well. Okay, and then over here, my base height pair is 2 and 3. So half of 6 is going to be 3. So this also has an area of 3. Okay, and then so I can just add up the area of those four triangles. So I get, this is for the whole kite. $15 and 6 would give me 21.5. Okay, there is an area formula for these two figures, which you can also use, but I just wanted to show you that you don't really need the area formula as long as you can remember the area formula for triangles, because they're just made up of triangles when you put in the diagonals. But there is an area formula. So the area of a rhombus is going to be 1/2 of diagonal 1 times diagonal 2. Okay, that actually just gives you the area of those four triangles, and it's the exact same thing also for a kite. So you're very welcome to use this formula, but just in case you blank out on it and can't remember it when you need it, it's just a bunch of triangles. Okay. All right, so let's move on to the next page. We're going to move on to regular polygons. Going to start looking at the area of regular polygons. Before we get to that, I want to remind you what a regular polygon is. That means all of the angles are congruent, and all of the sides are congruent. So in this figure, all of the sides are already marked congruent, but for it to be a regular polygon, this would also have to be true. Okay, so just a little vocab first. If I draw in the distance from the center of this polygon to one of the angles, say this one, that line segment is called a radius. So usually when we hear about radius, you think of a circle, but a polygon can also have the radius. It's still just the distance from the center to the outside, but it has to go to a corner. Okay? So if I draw in each radius, then that's going to cut this figure up into 5 slices, 5 triangles, and all 5 of those triangles are going to be congruent. Okay? So when we find the area of this later on, you can think of it again as just a bunch of triangles. And if you can find the area of one triangle, you can find the area of the whole polygon. Okay? So a little bit more vocab. This is called a central angle. Okay? And you can always find the measure of a central angle because if you think about all 5 of these slices together, it's 360 degrees. So I've got 360 total degrees, and since all of those triangles are congruent, it means it's just going to be a fifth. One central angle is going to be a fifth of 360. So the central angle is always going to be 360 degrees divided by the number of sides. Okay, so in this case, my central angle is going to be 360 divided by 5, and that's going to come out to exactly 72 degrees. Okay. All right, one more piece of vocab here. If you take a line segment that connects the center of the circle to the side, the shortest distance to the side, that would look like this. Okay, so it's going to be at a right angle. It's also, if we start with a regular polygon, it's going to divide that side in half like that. Okay, and this has a special name. It's called an apothem. Some people call it an apothem, usually apothem. Okay, so it's the perpendicular distance to the side. As opposed to a radius, which is the distance from the center to a vertex. Okay. All right, so there is an area formula for all regular polygons. This happens to be a pentagon, but this will work with a hexagon or a nonagon, any kind of regular polygon, but it has to be a regular polygon. So this won't work for, say, a rectangle where the sides, where the 2 sets of sides aren't congruent. The area is going to be equal to 1/2. I'm using a lowercase a here. So the lowercase a is for apothem. And the P is for the perimeter. Okay, so if you think about this, the perimeter is all of the bases all together, and the apothem is going to be the height of one of those triangles that make up the slices. So it's going to be all of the bases times the height, 1/2 of that. So that'll give us the area of all of the triangles together. Again, you don't really need the formula because you can always find the area of the triangles. Okay. All right, so let's look at this first example here then. So I'm going to find the area here. So I actually do use this formula when sometimes it's really easy to use it, like on this problem. So first off, I forgot to mark in that right angle there. Okay, so put a right angle in there. So I've got the apothem already. It's 6 centimeters. And then I don't have the perimeter, but hey, it's a regular polygon. I've got one of the sides. So since these are all congruent, I can find the perimeter really quickly. So the perimeter, it's a pentagon again. So there's going to be 5 sides where all of them are 5 centimeters. So the perimeter is going to be 25 centimeters. Okay. So then using the formula, my area is going to equal 1/2 of the apothem, which is 6, and the perimeter, which I just figured out, is 25. So I've got 1/2 of 6 times 25. That would be 3 times 25, which is 75. And again, this is square centimeters because we're dealing with area. Okay. All right. So on the next page, similar problem. We've got another regular polygon. This one's going to be a hexagon. The problem's a little bit tougher because we don't have nearly as much information. Okay. So looking at this one, I have the apothem. I definitely don't have the perimeter right now, and it's not going to be as easy to find it. So yeah, this is supposed to be, let's put that in, that was supposed to be a right angle there. So 8 centimeters is the apothem. I can see that this is a hexagon if you count up all 6 sides. So what I'm going to do here, when you don't have enough info from the beginning to get started with that formula, start thinking about cutting this into slices. Okay, I'm not going to draw all the slices of pizza here. I'm just going to do this one. They're all going to be the same. Okay, so if I can find the area of this triangle, then I'll be in good shape. Okay, so actually I'm going to draw one more radius in. So what I'm going to do first is to find one of those central angles, that one I just marked up there. Okay. So let's find the measure of a central angle. Okay, so in this case, I'm going to have 6 total. Well, what the heck? I'll just draw all of them in. So I would have 6 total slices there, right? So this is going to be 360 divided by 6. So that means that this is a 60-degree angle, okay? So once I have that, so I'm thinking of that like a whole slice of pizza in the middle as a 60-degree angle. So that means when I've got these half slices drawn in here with the apothem cuts this into half slices. So that means that this is going to be 30 degrees and 30 degrees, okay? And then let's look at this, this half slice over here. Hey, I've got 30 degrees, 90 degrees. So I can figure out that angle, right? The missing angle, 30, 90. This must be 60 then if I'm getting to 180. And so then this half slice here is a special right triangle. It's a 30, 60, 90 triangle, okay? I saw a screen that said find central angle. Okay, so the next thing I want to do is find a side length. Okay, and the way I'm going to approach that is to find this distance, because these two pieces are going to be congruent. Okay, so if I'm looking at a half slice, I'm going to find the crust on a half slice. Well, it's a 30, 60, 90 triangle. So hey, I've got, this would be the long leg here, right? And when I'm going from the long leg to the short leg, I'm going to divide by the square root of 3. So that means that this piece is going to be 8 divided by root 3. Okay? And I can put that in simple radical form. I can rationalize the denominator. So this is a throwback to a couple of chapters ago. This would give me 8 root 3 over 3. Okay? So if that's 8 root 3 over 3, then I can find this whole distance because there's just two pieces that are both 8 root 3 over 3. Okay, so the denominator would stay the same, right? So this is going to be 16 root 3 over 3 for that whole side length, okay? And now that I have a side length, now I can find the perimeter. Or I could just find the area of this whole slice and then multiply it by 6. It doesn't really matter. It's about the same amount of work. So the perimeter, well, my perimeter, I'm going to have 6 slices. They're all 16 root 3 over 3. So I'm just thinking 16 times 6, let's see, that's 60 and 36, 96. So this is going to be 96 root 3 over 3. Okay, and I can reduce that. That would be 30 equal 32 root 3. Okay, and now I have everything I need to find the area. Because I can use that perimeter. I already, that formula I have. I've got the apothem already. I found the perimeter. So this is going to equal 1/2 of the apothem, which is 8, that was given in the beginning, times the perimeter, which is 32 root 3. Okay, so 4 times 32 is 128. Okay, you could leave it like this. It would be that many square centimeters. You could also do a decimal approximation. So, you know, when I got to 8 over root 3, I could have made a decimal approximation there as well. And this would come out to about 221.7. Okay, so either way would be fine if you left it exact or as a decimal approximation. Okay. All right, and so alternatively, you could have found the area of the whole slice, but you still would have needed this this piece first and then the whole crust. So you could find the area of the whole slice and multiply by 6, or you can find the area of a half slice and multiply by 12, because there would be 12 half slices there. Okay. All right, moving on. So if you want to try this next one, it's actually a similar type of problem. It's a little strange looking. We're finding the area of a square, which is usually super simple, but the difference here is that we don't have the side lengths. If I knew the side lengths, I'd just do the base times the height, but I don't know the side lengths. All I know here so far is the radius. So it says that this is a square, which means it is a regular polygon. So I'm going to kind of think about it in the same way. So I'm going to draw in the rest of the radii here, so that I've got, it's like it's a, you know, it's a little Caesar's pizza or something, right? I got 4 slices like that. So I can find a central angle. So I'm thinking, all right, the central angle, well, there's 4 slices, just like that. So 360 divided by 4, hey, this is a right angle then. Okay, so I've got a right angle in there. Okay, so I'm going to take, it doesn't matter which one you do this with, but I'm going to use this slice since I've already got the 3 marked there. And I'm going to cut that into half slices like so with the apothem. Okay, and if this was 90 degrees, then that means I've got 45 degrees and 45 degrees. That 90, if you cut it in half. Okay, and then when I'm looking at a half slice, hey, 45, 90, that means this must be 45 as well. Okay, or I could say the same thing down here. Okay, and then, hey, it's another special right triangle. So when you have the hypotenuse on a 45, 45, 90, you're going to divide by the square root of 2. So that means this piece would be 3 over root 2. Okay. All right, and then let's see, let me simplify that. So that's 3 root 2 over 2. And that means that this is also 3 root 2 over 2. Okay, so that means when I'm looking for one of the sides, I'm just going to use this up here because all 4 sides are going to be congruent here, right? I got 3 root 2 over 2 plus 3 root 2. Oh, it's off screen there again. Sorry about that. I just took that and put it in simple radical form, okay? But if this is 3 root 2 and that's 3 root 2, well, that's going to add up to 6 root 2 over 2. And that would simplify to 3 root 2. So that means the sides are 3 root 2. So this side would also be 3 root 2. And now I've got enough to find the area here, right? Because I've got the base and the height. I've got 2 of the sides of the square, so I just multiply them together. So I could find the perimeter, but I'm not going to bother with that. I'm just going to think the area of, I should really use a lowercase b, the area of a rectangle is base times height. Not of a, this is a square, but base times height. The base and height are both the same thing here, since this is a square. Okay, and then to multiply this together, I'm going to do 3 times 3. That gives me the 9. So I'm doing the pieces on the outside of the radicals, and then I'm going to multiply the 2 radicals together. So root 2 times root 2 would be the square root of 2 times 2, right? Root 4. Okay, and the square root of 4 is 2. So then my area would be 18, and I've got centimeters, so this would be 18 square centimeters. Okay. All right, so I don't have a problem with a regular triangle, but you might see that on your homework. So I just want to really quickly show you how if you have a regular polygon that's a triangle, that means it's going to be equilateral, right? And also equiangular. So if you have a problem where you've got either the apothem or like a radius, you could also think of this as cutting that up into a pizza. You'd have 3 slices like that, okay? And that's going to be 1/3 of 360. So this would be 120 degrees. And that means when you cut up, if you were to cut this into half slices like that, well, the half slice at the middle would be half of 120, so it would be a 60-degree angle. So hey, 60, 90, 30. So again, you'd get a special right triangle. Your half slice would be a 30, 60, 90. Okay. So if you have a hexagon or a square or a triangle and you cut it up, you're going to get special right triangles. But that's not going to be the case with all of the figures. So next we're going to look at a pentagon again. We did a pentagon already, but we already had enough to find the area, the perimeter, and the apothem from the beginning. So this last problem is going to be a little bit trickier because we're going to have to cut it up into slices, and it's not going to work out as nicely with these special right triangles. Okay, so let's take a look at this one. I'm going to find the area again. Again, this is supposed to be a right angle down there. Okay, so finding the area of this regular pentagon. So I'm going to start the same way I did with the last couple problems. I'm going to draw in my radii, so I get my slices of pizza here. And I'm going to start with one of the angles. So this is going to be 360 divided by 5. Since there's 5 slices like that, that's going to come out to exactly 72 degrees. Okay. So then with my half slices that I have down here, I'm going to take half of 72. So that means that this is going to be 36 degrees and 36 degrees. Okay. So looking at this half slice, this is not a special triangle. I could find that missing angle, but it's definitely not going to be a 30, 60, 90 or a 45, 45, 90. Okay? But that's okay. I can still deal with this. Okay, I can find the perimeter really quickly because all of these sides are 8. Okay, so the perimeter is no problem, but I need to find the apothem in order to use the area formula. Okay, so remember there's the formula I'm working with. So perimeter, yeah, let's just get that right off the bat. Perimeter is there's going to be 5 times 8, so 40 centimeters. Okay. So I got that piece. So most of my work is going to come from finding the apothem. Okay. So I already kind of got started on that by finding the central angle and then cutting it in half. All right. So let's call this, well, I'll call this A for the apothem right here. Okay. Now what I can do with this triangle, I know the whole crust is 8, and the apothem on a regular polygon is always going to cut that slice in half. So then I know that this is 4. Okay. So let me draw this separately, just so there's less to distract me here. If I had a problem like this and I asked you to solve for A, well, you got to think back a couple chapters. We can do this with trigonometry. Okay. So you got to think about, all right, this is my perspective. I'm up here at this acute angle. This would be the opposite leg, and this would be the adjacent leg. So I could set up a trig function using tangent, think SOHCAHTOA. Okay, so that I could say the tangent of 36 degrees is going to equal opposite over adjacent, so 4 over A. Okay, and now we can use the incredible switch. I'm going to swap those two because that's going to isolate the A. Okay, and now I can use my calculator to figure out what 4 divided by the tangent of 36 degrees is. Okay, and you're probably in degree mode, but if you're not, you want to make sure you are in degree mode because our angle there is in degrees. So I'm hitting mode. I can see I am in degrees. Okay, so 4 divided by the tangent of 36 degrees is about I'll call it 5.51. It's approximately 5.51. Now I found the apothem, right there. So now I have something that I can put in there, and I should say this is not exact anymore because that number is rounded. Okay, so I'm just going to use that whole decimal in my calculator if I can get it to stop shining there. So I'm going to multiply that by 1/2 or 0.5, and then multiply that by 40. And so I'm going to get about 110.11. Okay, and again, this was in centimeters, so this is area. It's that many centimeters squared. Okay, so there's a lot of steps here because you got to cut it up, find the angle, then you got to set up a trig function using SOHCAHTOA. So you got to bring in some stuff from some previous chapters in order to solve problems like this. Okay, that's all I have for today. All right, see you next time.